All right, this is section 6.4, number 34, and we're asked to compute the amount of work it took to build one of the Great Pyramids. Let me go ahead and read through this very quickly. We have a square base with side length 756 feet. That's at the base. And when it was built, it had a height of 481 feet. Oh, that's kind of cool. A little bit of history there. The density, which we're going to need, of limestone is about 150 pounds per cubic foot. So that kind of helps us figure out how heavy objects are, what the forces are. Estimate the total work done in building the pyramid. Well, let's kind of draw a picture here, a side view. I'll scroll down to do that. It's something like this. I already forgot what the base was, 481 feet. Is that right? No, 756 feet is the base. So 756. And we know the ultimate height of this when it was originally built was 481 feet. So this height here is 481 feet. And we are just going to take a slice out of that and lift it up. So let me just get a representative slice going. Here's a representative slice. Again, this is going to be the side view, but that's a delta y there. Let me go ahead and write in here side view. And we need a top-down view. Well, the top-down view actually of that slice, and I'll keep it in red, is going to look like this. So this is a square. And it is some width. We don't know what this width of this slice is, but I happen to know that it's twice this distance. I'll call x sub I. So it's twice x sub I here and twice x sub I there because it's a square and therefore it's of area 4x sub I squared. Now our job is to find the x sub I. Very common tactic, as I've mentioned in class, is to use similar triangles. You could also have built an equation for the edge here, but I'm going to go ahead and use similar triangles to show that technique. I'll slide off to the side here, and I'm going to take that triangle, and I'll do this in black here. And unfortunately, I don't have a tool that actually draws a nice triangle, so that's just my hand. That will draw that. And let's see. We know that the height of this triangle is 481. Its width across is half of 756. That's 350 plus another 25 is 375 plus another 3 is 378. 378. Yeah, I think that's right. Okay. And so we're going to go ahead and draw our slice in here. And we know this is x sub I, and we know the distance here is some y value, our current height. Well, we can actually look at two triangles then, because you have this outer triangle, which I'll go ahead and showcase with a highlighter here. You have this outer triangle edge, okay. And then you have an inner triangle that's similar, and I'll go ahead and use a different pen color for that. You have this inner triangle, trying not to overlap it too much, but those are similar triangles, those two right there. So I happen to know the full side length. Oh, that was supposed to be a 481. I don't know why it looks like a 448. Let me go ahead and fix that. 481. Anyway, we have this full side length of 481 is to 378. So 481 is to 378 as the side length of just this smaller triangle, that little side length. Well, that little side length would be 481 minus y sub I. It is almost the full length of the height of the triangle, but you're less by amount y sub I. So 481 minus y sub I is that distance, and then the x distance is x sub I. And this allows me to solve either for y sub I or x sub I, but I don't know which one I want to solve for yet. Let's go ahead and go back here and just get the volume of that ith plate. This ith plate here, we can compute, has volume, area, times width. Well, that's not going to work when we plug that into an integral and start stacking those plates. You need to find out what x sub I is, and luckily we have a relationship right here between x sub I and y sub I. We know that x sub I is going to be 378 over 481 times 481 minus y sub I. So I'm going to go ahead and insert that into this formula. 4 times the quantity, 378, oops, supposed to be an 8, over 481, quantity 481 minus y sub I and quantity squared, delta y. That is the volume of that slice. Now, I knew I'd have to find the volume, even though I didn't really talk about why. I just knew that at some point we're lifting some stuff up this far, right? So let's now talk about the rest of this. So the force, remember, the energy used to move a whole entire layer is the weight of that layer times the distance you're moving that layer. The weight is a force, and the distance is just some distance that we're going to move it. Now, this is where this problem is slightly different than all the other problems, because if you look at this pyramid, I am not moving this layer right there all the way to the top. That's actually not happening. I actually move that layer from here to here, from the ground to that top. And in fact, the biggest layer, the layer on the ground, didn't get moved at all. That layer did not get lifted. So each of these layers gets smaller and smaller as we lift them up. And going back to the picture, that makes sense, right? The very tip top there is the least amount of work. You have a very small amount of rock lifted up kind of a large distance, but it's a small amount of rock. So the force is less. The distance is greater, but it's a much less force. The force is much less, so it doesn't take as much energy to move that upper rock. Okay, so to move this ith slice, the distance we're moving it is just this guy right here, which is y sub I. We're moving it y sub I, not 481 minus y sub I. And that usually throws people off with a problem like this. You have to think about the slice itself. So it is the force on the ith slice times y sub I. Well, the force is the mass times acceleration due to gravity. And you can think of this as a fluid in a way. Solids can be thought of that way if you have objects that weigh something a little bit different. You can say, well, okay, I have a volume, which in some ways you can think of as a mass. It's not really, because a volume is in cubic feet and you want to turn it into pounds. So you have a volume, but that's in cubic feet. And I want to turn that into pounds. Well, they gave me something for the density of this. The density of this rock is, that's limestone, but the density of the limestone is 150 pounds per cubic foot. So I know I'm lifting V sub I cubic feet, and each of those cubic feet is 150 pounds. So it's 150 pounds per cubic foot. That's the units. So if I did the cancellation there, I'd get feet, or I'm sorry, I'd get pounds, sorry. And then times y sub I, and the units for our distance is feet. So if you look at that now, that all those units will cancel to foot-pounds. So that is actually a work. Let's go ahead and insert the V sub I here. So remember, it's 150 times V sub I, so that 4 is going to multiply that to become 600. We have some quantity 378 over 481 times 481 minus y sub I and quantity squared, and then we have y sub I delta y. Let's just double check. I'm just quickly looking through. Yes, so that's the work to lift the ith slice. And again, if you think about this, if you're near to the top, let's say you have a slice at the 480th foot, well then that means if it was 480 feet is where that slice is, you lifted it 480 feet to get there, and it weighs 481 minus 480, or 1 times 378 over 481, or basically it weighs very little because it's the tippy top. So this should make sense to us now. So let's go ahead and compute the total work done to build this pyramid. Total work done, we're going to lift from y equals 0 to y equals 481, and it's going to be our work formula here, which is 600 times, and I know that's a constant squared, so I'm going to write that as 378 over 481 squared. And then I have, let's see, 481 squared minus twice 481 times y plus y squared times y dy. And now this is just polynomial, and I will fast forward just so that I can get this computation done and out of the way. And I'm just showing the halfway point here of the computation. I'm just about to insert the upper and lower limits and evaluate, and that's going to require some type of calculator for me. So I am going to go ahead and do that. And we get 1.653 times 10 to the 12th, or 1.653 trillion foot-pounds. That's a lot of energy required to build this. But then again, it should make sense that it requires a lot of energy because, well, it's a very huge structure. And now kind of the end question here was, if each laborer worked 10 hours a day for 20 years for 340 days per year and did 200 foot-pounds per hour of work in lifting the limestone blocks into place, how many laborers were needed to construct the pyramid? This is kind of what we call back-a-napkin math, where you make some broad generalizations just to see how long it took to do something, or how many people did this. So let's see, we have people working 10 hours a day. We're going to assume, again, 340 days per year. So that's 3,400 hours per year, right? That's how many hours per year a single person would work. And then they do that for 20 years. So this is how many hours total that a person would work. Let's see, that's 68,000. Nope, that is not 68,000. Yep, that is 68,000. I don't know why I didn't think it was. So that's 68,000 hours total that a single person would work. And a single person, let's see, we have 200 foot-pounds per hour that person worked. So if you take that number, 680 or 68,000. I keep saying 680, but I don't mean that. It just means 68,000. If you take that 68,000, 34, 68, yeah, 68,000. I don't know what is going on with my brain. If you take that 68,000 hours and you multiply it by the 200 foot-pounds, let me move this over, 200 foot-pounds per hour, those cancel. And now we have a very large number. Let's see, doubling it up, 136, and we have 1, 2, 3, 4, 5 zeros, or in other words, 1.36 times 10 to the 7th foot-pounds in a worker's lifetime. That's how much they can commit to this task. So let's see how many workers it takes. We're going to go ahead and foot-pounds, I should say, per worker. Okay, we're going to see how many foot-pounds it takes. And the way or how many workers it takes. The way we do that is we take the total energy required and we divide that by the total energy used per worker. I don't know if it was 36 or I can't remember. 1.36 times 10 to the 7th. And that's foot-pounds per worker. And that will actually, the mathematics will cancel here, and the word worker will go up to the top. And so doing the calculation, we get roughly 121,536 workers. That's quite a few people for something that happened a long, long time ago. And all those people are working 10-hour days, 340 days a year for 20 years. That is a monumental amount of energy expenditure and a lot of workforce.